Good evening, everybody. The weird world of the very, very small. Looking not at the very large, which is what I normally do for astronomical topics, but here looking at the very small. So we'll be starting with just a little bit of a sense of scale, talking about sizes we're familiar with, down to the very small, and then asking ourselves, how do we know what the world is made of? A sense of symmetry gives us an idea of the underlying structure of everything around us. And then I'll be looking at the quantum world with a few different examples, including how we actually see atoms with microscopes. So the scale we're used to, from meters down to, let's say, millimeters, that's the sort of thing that we can deal with. We can see objects down to millimeter sort of size. If we want to go much smaller, perhaps you recognize that, perhaps you don't, that's a pollen grain. That's about 1/20th of a millimeter across, or 50 microns, because a micron is 1/1000th of a millimeter. So that's rather tricky. We would barely be able to make that out as anything but a speck. That's nature, but we can actually make things on that sort of scale. It is possible to manufacture, for instance, a gear train or cogs on a scale much smaller than a millimeter. Why we would want to is another matter, but we are capable of doing that. But the really, really small scale starts when we start thinking about electronics rather than mechanical systems. So these days, for instance, microprocessor chips, the areas might be measured in square millimeters, but those square millimeters can contain hundreds of millions of transistors. So the sizes of individual components on a computer chip, doesn't really matter whether it's a microprocessor chip or a memory chip, it really doesn't matter. The individual components are getting down to the nanometer size, where a nanometer is 1/1000th of a micron and a micron is 1/1000th of a millimeter. So we are getting down to something not much bigger than an atom when we start talking about the smallest things that we can possibly manufacture. And we get the feeling that there must be structure down there. We've known that for a long time, but you can still ask the question, what is the world made of, and how can we tell what it's made of? What clues do we have? Or if perhaps you think of it in terms of what clues did we have that made us think about how the world is put together and the concept, eventually, of atoms, the building blocks of all matter. So you could say it all started with Aristotle, who said everything is just earth, air, fire and water. Well, yeah, that's a very simplistic way of looking at the world, and of course it works to a certain extent. You can talk about the fire content or the air content of certain materials, but it doesn't work when you start to get more sophisticated. Then along comes Galileo, who says we should determine the nature of the world around us by experiment, not by intellectual argument. In other words, we should ask the question, not what should happen, but what actually happens. So we shouldn't say, I think the world ought to be made of something. We should actually do experiments, if possible, to find out what the world is made of. And then came along Newton in the 1600s, who gave us laws of motion, how things behave when they move, the law of gravity, the universal law of gravity. He told us about the nature of light, and invented essentially, or at least formulated, what we now call classical mechanics, or often simply Newtonian mechanics. The idea that if you move an object, it'll accelerate, and all objects attract each other through gravity, depending on the mass and depending on the distance between them. So basically Newton was describing a clockwork universe, and you can think of that in terms of the planets going round the sun. You wind them up, set them off, and they just keep going like clockwork, as if they had a mechanism underlying them. But when we look at the world around us, we get clues. For instance, look at snowflakes. They are all sixfold symmetric. Every one appears to be different, but they are all sixfold symmetric. You could take any of them, rotate them 1/6 of a revolution, and they look essentially the same. that must be telling us something about the underlying structure. The structure of a crystal, a macroscopic crystal that we can see, must be telling us something about the microscopic structure inside. Whatever building blocks make a snowflake, the factor of sixfold rotation must be important. And we see that in different crystals. Here's a piece of metal that's been melted, and then when it solidifies, it recrystallizes into this particular shape. This shape must be telling us something about the underlying building blocks, how they fit together. And whenever we see a material like this, for some reason, the building blocks want to be arranged in a sort of cubic arrangement. And there are some materials like this dodecahedron crystal. This is not an element, it's an alloy of different elements. But again, if it wants to crystallize in this particular shape, this has not been manufactured, this is the crystal shape that it wants to adopt, then that must be telling us something about how the atoms or the building blocks, which we eventually started calling atoms, how these building blocks are put together. It must be something to do with five-sided pentagons, because that's how it chooses to make a crystal. So we have these clues. Macroscopic shapes tell us something about the underlying structure, but it took us a while to figure what that underlying structure was. I'm not going to go through all the detail, but our understanding of atoms as the building blocks of matter started way back with Democritus, way off the left-hand side of this diagram. But throughout the centuries of the 16, 17 and 1800s, a number of different scientists contributed to our understanding. Boyle, Newton, Lavoisier, and then along came Dalton, Avogadro, Maxwell and Boltzmann. I'm not going to talk about their individual contributions, but throughout these centuries, various scientists, especially chemists, were putting together ideas of if you react A with B, you get C, and from those sorts of reactions, you can start to piece together what are the individual building blocks of the materials or the compounds that you're playing around with. In the 1800s, there were a couple of physicists who made important discoveries. Young looked at the nature of light and determined it was a wave. Waves are different from particles because waves can interfere with each other. You can imagine troughs and crests of a wave. If one wave meets another, the trough of one wave might meet the crest of another and cancel out. So the idea of things cancelling out or reinforcing each other is a wave property, and Young showed that light has wave properties. So in the early 1800s, it was decided that light is a wave. And various other rays that had been discovered throughout this time, it was realized radiation, radioactivity, alpha, beta and gamma rays. It wasn't originally known what they were, but after a while it was realized, well, actually these are particles. I'm not going to be talking about alpha particles, but beta rays turned out to be what we now call electrons, and electrons are particles according to J.J. Thomson. So in the 1800s, we thought we had a reasonable idea that building blocks are made of various particles, including electrons and presumably something else as well that hasn't yet been discovered. But atoms are made of electrons and other things, and light is a wave. So all of that seemed reasonable at the time. But come the 1900s, well, all hell let loose, basically. Again, a number of different scientists made contributions over these decades. Some of them you may recognise, others not, perhaps. Becquerel, who discovered radioactivity, Planck, Rutherford, who discovered the nucleus of an atom, and then Einstein and Bohr, then de Broglie, and the architects of quantum mechanics, Heisenberg and Schrödinger. So there was an awful lot going on in these first few decades. These 3 decades of the 1900s arguably were even busier than the previous 3 centuries in terms of how much was being discovered about the building blocks of matter. I'm not going to go through all the details, but as well as the discovery of radioactivity, some rather confusing results started to arise. For instance, although it had been established last century that light was a wave, Well, along comes Max Planck and says, well, no, you can think of light as a particle. Not only that, but a little later on, de Broglie says, yes, we know electrons are particles, but actually, yeah, they also behave like waves. So there was a huge amount of confusion. Is light a particle or a wave? Is an electron a particle or a wave? It seemed like a perfectly sensible question originally, but now it's getting very confused. We don't actually know the difference between a particle and a wave because different things seem to behave in different ways. This is getting very confusing. And it wasn't until roughly 1930 that Heisenberg and Schrödinger started to pull together all of these strands of evidence, the observational evidence, the experimental evidence of what we think the building blocks of matter are, these atoms which appear to have a nucleus, according to Rutherford, and appear to have electrons, according to other experiments. It wasn't until Heisenberg and Schrödinger started to pull together a mathematical framework to describe the building blocks of matter that we started to get a handle on this problem. So we all tend to think of an atom as being, well, okay, it must look something like that. It's a positively charged nucleus in the middle and a whole load of negatively charged electrons buzzing around it. It's the sort of classical, sort of iconic picture of an atom. Well, it's a nice picture, but it's misleading for all sorts of different reasons. Not least, if you look at this particular picture, it gives the impression that all the electrons are essentially the same. They don't seem to be orbiting the nucleus in quite the same way, but if you were to take this picture and rotate it slightly, then all the electrons are effectively the same sized orbits and going around the nucleus at the same speed, and therefore they're all behaving the same way. But actually it was established quite a long time ago that in atoms all the electrons behave rather differently. And we should think perhaps of the electrons not in terms of all orbiting the nucleus in the same way. Perhaps it's better to think of the electrons in different sized orbits. So the picture at the top still looks a little bit like a solar system, but we have, if you like, more than one planet in each orbit. So they're coloured here just to make them easier to distinguish. But it's still a wrong interpretation in terms of it being flat. It's much better to think of atoms as being three-dimensional objects, so the electrons aren't orbiting the nucleus like planets in a solar system. It's more like they're moving around in the shell, as indicated by the bottom picture, where each shell has been cut in half so we can see the shells inside. This is better. This picture of concentric shells is better than the previous model because at least it shows us that different electrons are at different distance from the nucleus, and that explains why they have a different energy, and that in turn explains why lots of different atoms have different properties. It's because of the way the electrons are configured in atoms. So it's still not a great picture, but it has a few redeeming qualities in terms of explaining some properties of atoms. And from that idea, we can then start to understand why different elements in the so-called periodic table have the properties they have, and indeed why it's periodic in the first place. In other words, why do certain elements, like for instance if we look on the right hand side, various gases like fluorine, chlorine, bromine, iodine, they are arranged vertically because they have similar properties. And similarly, if we pick another one at random, the metals lithium, sodium, potassium, rubidium, they're in a vertical column because they have similar properties. And we get that from the way electrons are arranged in atoms. So as soon as it was understood that we have a nucleus, a positively charged nucleus, and negatively charged electrons arranged around the nucleus in shells, then it started to make sense why particular elements have their particular properties. And this is various properties. It could be mechanical properties, it could be electrical properties, it could be magnetic properties. All of them are explained by what the electrons are up to. So could we say, well, okay, should we think of an atom as being a sort of solar system, just like planets orbit the sun at different distances? Can we say electrons orbit the nucleus at different distances? Is that a good analogy? Well, it is an analogy, and it's sometimes a picture we have in our heads, but it's actually not a particularly good analogy. Mainly because electrons don't follow orbits around the nucleus in the same way that planets do. We should really think about asking the question, where is an electron likely to be found? So an electron really exists in a sort of a cloud around the nucleus, and we can ask, where is that electron likely to be found? And for instance, if we come to this particular picture, here's 8 representations of how an electron might behave in an atom. In this one, in all of these, the nucleus is in the center of this particular pattern, and the cloud, the grey smudge, in this case above and below the center, the smudge is telling us how likely are we to find the electron at any particular position. So in other words, we're very unlikely to find it right in the middle. We're quite likely to find it either in this position above center or this position below center. And as we go further and further and further away from the nucleus, it's getting darker and darker and darker and darker, indicating that we are less and less and less likely to find the electron in this position. So there is no absolute position of the electron in the same way that there is a position of a planet orbiting the sun. All we can really talk about is the likelihood or the probability of finding an electron at some location close to the nucleus. And depending on which electron we're talking about, the cloud looks very different, as in the 8 examples I've given here. So when we're dealing with atoms, we have a problem. We can use words and we can start talking about electrons are particles, and they move in orbits and they spin and they have a certain amount of energy. But the problem with using English words is that English words often have more than one meaning. So when we talk about the spin of an electron, it's very tempting to think of that as being the same thing as the spin of the Earth. It's spinning on its axis. And when we talk about an electron orbiting the nucleus, it's tempting to think about a planet orbiting the sun. But they don't behave the same way. And using words that have connotation, that make us think of other things, is confusing. We don't even have a decent definition of particle and wave, because now it appears that electrons are particles and waves, and light is a wave and a particle. So the meaning of those words starts to get very blurred. So maybe we should abandon trying to explain atoms in terms of English words. What's the alternative? Well, we can start drawing pictures. We've already established that thinking about dots moving around a nucleus is not very good. And perhaps we ought to adopt this idea of, well, we can think of them as clouds. But that is really only a way of trying to represent the true nature of an electron. We're just saying that the behavior of an electron depends on the probability of finding it in some location, and if we choose to make this particular representation in the bottom right, we can draw a picture that represents that probability. But the picture itself is not actually a picture of the atom. It's a picture that, in a sense, describes the behavior of the atom. So if words aren't very good for describing the very, very small, and pictures aren't particularly good either, what should we be using for describing the building blocks of everything around us, the building blocks of matter? What do we need to describe atoms? Neither words nor pictures. And you're not going to like the third option. The third option is maths. Maths, particular equations, particular ways, particular mathematics that describe how things behave, does allow us to describe the behavior of atoms, the properties of atoms. But we still, of course, have a problem. Even though it seems to be true that mathematics describes the world of the very, very small, If we want to, for instance, teach that mathematics to a whole bunch of students, well, we have to use words, and it's nice to use pictures to try and describe what we're talking about. So arguably we have to use words and pictures, but the only true description of an atom is maths. And that's why teaching quantum mechanics or quantum theory at university level is so tricky. It's not just a question of throwing difficult concepts at the students. We also have to teach them the maths they need in order to deal with those concepts. And the maths is not easy. It is not the sort of maths that you learnt at school. You have to learn different ways of handling descriptions of objects that you have to try and keep in your head that aren't, in a sense, real. You've always thought of atoms as being actual building blocks, but when you start describing them at atomic scale, they become rather more nebulous and rather more difficult than the sort of concrete examples we're used to. So, yes, unfortunately, we have to deal with maths. Yeah, I know, nobody likes that idea, but yep, you've got to deal with the maths. Heisenberg and Schrödinger realized this when they started to put quantum theory together and try and pull together all of the disparate strands back in the 1930s. Heisenberg said, "We wish to talk about the structure of atoms, but we cannot talk about atoms in ordinary language. There's this problem with every word we use having more than one meaning, and we can apply it to an atom for sure, but we have to remember that if we're using a word which is used in another connotation, we have to be careful." It's like saying, don't use any words with any baggage or preconceptions. Rather than talk about electrons orbiting and spinning in an atom, perhaps we ought to really say, the slithy toes did gyre and gimble in the wabe. Because those two red sentences contain exactly the same amount of information. Neither makes any sense at all unless you define very clearly what you mean by an electron, what you mean by orbit, what you mean by spin, what you mean by atom. Just like the last sentence doesn't make any sense unless you know what a tove is, or a gimbal, or what indeed is a wabe. But of course it's too late. We've been using quantum theory for 100 years and we are used to using the language that was developed 100 years ago, and it's too late to change now. So although electrons don't spin in the same way that the Earth spins, we still have that word to describe the property of electrons, and we just have to get used to the fact that it doesn't mean quite the same thing that we're used to that word meaning. Bohr, one of the architects of how you'd think about putting atoms together, said this: "Everything we call real is made of things that cannot be regarded as real." In other words, the world around us appears to be absolutely solid and concrete, and we can bang our fist on the table and say, yep, that is quite definitely real. But it's made of atoms, and atoms are very nebulous items, objects, if you will. And so we have this rather interesting paradox that something that is effectively ethereal makes up things that we regard as solid and real. Schrödinger said this: "Atomic physics has shown that atoms have no meaning, but can only be understood in experimental measurement." That's a hell of a thing for any physicist to say. Atoms have no meaning. What he meant was that quantum theory, which explains essentially how everything works at the very small level, and if you put lots of small things together you get big things, but the explanation of how things work can only be put together by a mathematical construct called quantum theory, which allows us to ask the question, if I were to measure this, what am I likely to get? If I were interested in how much energy is in this hydrogen atom or this hydrogen molecule, then I can do the experiment and quantum theory predicts what I should get as an answer. Does it actually tell you what an atom looks like? Well, sort of, no. But it does allow you to figure out how things work. I don't like it. And I'm sorry I ever had anything to do with it. That's, again, an amazing statement for the architect of quantum theory. None of the people who were putting these things together 100 years ago really thought they necessarily had things right. They simply said, here's a way of building a theory which apparently explains what atoms are, what molecules are, and how they behave. But they struggled with some of the interpretation because ultimately it's a weird theory. It gives predictions which seem to go against common sense, hence the I don't like it. People wanted to build theories which agreed with their gut feeling, but quantum theory does not agree with your gut feeling. There are plenty of examples where quantum mechanics differs from common sense. One of the principal ones is that atoms, and that by inference that means basically all subatomic particles, all atoms, all molecules, essentially anything, is unpredictable. In other words, we can only talk about the probability of, let's take an atom as an example, we can only know the probability of an atom having a particular property, let's say where it is, or how fast it's moving, or how much energy it has. We can never say this is absolutely the case, that atom A is sitting here with a speed x and an energy y, etc. The best we can do is to say the probability of it being in this particular state with these particular properties is this, and we can calculate that using quantum theory. We tend to think of atoms as being small, but actually they don't have a size as such. If we talk about an electron having a probability of being found at a particular location, it is quite likely that in a particular atom, an electron is quite likely to be found close to the nucleus. But it could be further away from the nucleus. It could be 1 nanometer away from the nucleus. It could be 10 nanometers away from the nucleus. Lower probability the further you go, but the probability doesn't actually go to zero. It just gets smaller and smaller and smaller as you go further and further and further and further from the nucleus. So when you talk about an electron in an atom, well, really, the electron could be anywhere. It is simply very unlikely to be a long way from the nucleus, and it is very likely to be close. Excuse me. So you can't really define how big an atom is, even though we tend to think of atoms as small because they tend to bunch together quite close to each other in a solid material, for instance. That simply means that atoms overlap. It doesn't mean that they're small. Again, it goes against common sense. Atoms can be in two states at the same time. If we think of, for instance, spin, an electron can spin clockwise and anti-clockwise at the same time. That makes no sense whatsoever. If we think of the Earth spinning, we know it spins from west to east, and it only spins in that one direction. It doesn't ever decide to spin east to west, and it certainly can't spin west to east and east to west at the same time. It goes one way. If it was hit by something large enough, it might decide to spin the other way, but it's only one thing at a time. And yet, when we look at the weird world of the very, very small, subatomic particles and atoms and molecules, it looks like they can exist in two states at the same time, even when those two states seem to be contradictory. It must be either one or the other. So there's lots of reasons why quantum mechanics doesn't make any sense whatsoever. Einstein said common sense is the collection of prejudices acquired by age 18. What he was really saying is that quantum theory goes against common sense. But that's because common sense is simply our view of the world, ignoring quantum theory. And of course, when we're young, we're trying to make sense of the world by looking around us and seeing things and tasting things and hearing things and using our senses to try and make sense of the world. Only when quantum theory comes along do we realise that it's at odds with quantum theory. And the bottom line is quantum theory has made an awful lot of predictions which have gone against the idea of common sense. But whenever we've been able to test quantum theory, it's been right. In other words, whenever there's a conflict between quantum theory and common sense is wrong. And that takes a little bit of getting used to. This idea of heads and tails, that everything is based on probability rather than absolute ability to predict the future. Einstein said God does not play dice. God is subtle, but he is not malicious. Einstein didn't like the idea of quantum mechanics saying that everything has a probability of occurring, but there's no way we can predict what's actually going to happen. Hence the famous expression, God does not play dice. Bohr was completely against that and basically told Einstein, stop telling God what to do. If that's the way the world is, that basically the world is based on probability, not on absolutes, then get used to it. The fact that you don't like it is neither here nor there. That's the way the world is. Let me deal with 3 aspects of quantum mechanics to give you an idea of just how weird things can be. Firstly, the fact that the order in which things happen can matter. Secondly, Schrödinger's cat, and then we'll look at how quantum mechanics can be used to see atoms. So firstly, the idea that order matters. Now, I'm sure you're aware that in algebra, A times B is the same as B times A. In other words, 2 times 3 is the same as 3 times 2. Doesn't matter which order you put them, one thing multiplied by another gives you the same answer. But in quantum mechanics, if A and B represent not just numbers, but things that we can measure, like we're interested in the position of an object and we're interested in the speed of an object, if that's what A and B represent, then the order in which we do things does matter, because A, B is not the same as B, A. Okay, you say, right, that's just a quirk of mathematics, so what? Well, it matters in a way that I can illustrate by imagining what if the rules of quantum mechanics applied in the world that we can see around us. We think the rules of quantum mechanics ought to apply, but we don't see them in this form. Let's imagine that we had a zoo, or a park if you prefer, that was occupied by 4 different types of animal. The top pair are carnivores, lion and vulture, and the bottom pair are vegetarians, a waterbuck and an ostrich. So there's the carnivores, there's the vegetarians. But we can also split them in a slightly different way. We can say that the left pair are 4-legged animals, the lion and the waterbuck, and the right pair have got wings. Yes, I know the ostrich can't fly, but it still has wings. So we've got 4 animals that can be paired up in different ways. Let's imagine that we wanted to select an animal, and we're going to select it by deciding if it's a carnivore or a vegetarian and how many legs or how many wings it has. Right, we're going to first pick 2 out of the 4. So, for instance, let's imagine we do it in this order. We're going to pick 2 out of the 4 by first separating out the vegetarians from the carnivores. So we're going to go into the park and we're going to round up all of the vegetarians, and we're going to take those vegetarians and put them in a separate corral. Now that we've got the vegetarians separated, we're going to make another choice. From those, we're going to pick again. And this time, we're going to pick the 4-legged animals from the vegetarians we've just rounded up. We would expect, on picking the 4-legged animals, to get the waterbuck. But what we actually find is not just the waterbuck. We find we've got the waterbuck and the lion. Even though we picked out the vegetarians first, took them to one side, and then picked the 4-legged animals, somehow the lion is back. That does not happen in the macroscopic world that we understand, but it's happened here. Not only that, but the order in which we separate the vegetarians from the 4-legged animals matters. Because if we pick a different order, let's first pick the 4-legged animals. So we go into the park and we round up all the 4-legged animals and we take them to one side and corral them off separately. And then from that batch of animals, we pick the vegetarians. So again, we expect to only pick out the water buck. What do we actually find? We get water bucks and ostrich. Even though we first picked out the four-legged animals and took them to one side, somehow the ostrich is back again. This is how things behave in the weird world of the very, very small. It makes no sense in terms of figuring out that shouldn't happen if we're rounding up animals, but that, as an analogy, is what happens in the world of the very, very small. Second example is this weird one called Schrödinger's cat. So what we're going to do here is kill a cat. Oh yeah, okay, don't worry, we're not actually going to kill a cat. We're just going to do a thought experiment. We're going to put a cat in a box. And the thinking goes, according to Schrödinger, he said, imagine what if we put a cat in a box and then we decided by an autonomous robot whether or not the cat would die or not. Let's say, for sake of argument, we have a radioactive atom which has a 50-50 chance of emitting some radiation which is picked up by a Geiger counter. We're going to put all of this equipment in a box and seal the box so we cannot see what's going on. But after a certain length of time, that atom has a 50-50 chance of radiating a particle which is picked up by the Geiger counter. The Geiger counter then tells this robot with a hammer in its hand, its arm, to smash a vial of poison, which then would kill the cat. So there's a 50-50 chance of the cat being alive or the cat being dead. But in this thought experiment, the box is kept closed. And the atom, after a certain length of time, can be in two different states at the same time. It might have decayed and spat out a radioactive particle, or maybe not. And it can be in both of those states at the same time. Which means the Geiger counter can be in two states. It has picked up or it hasn't picked up the radioactive decay. Which means the vial of poison has been smashed and hasn't been smashed at the same time. Which means the cat is alive and dead at the same time. It is not simply a question of the cat is one or the other, but we don't know which until we open the box. That's not what's being said. In quantum theory, you can be in two states at the same time. So if the atom can be in two states at the same time, according to this experiment, the cat can be in two states at the same time, providing we don't open the box. That is the paradox of Schrödinger's cat. As long as the box stays closed, the cat is dead and alive at the same time. At some point later, we may choose to open the box, at which point the cat becomes dead or the cat becomes alive. But before we open the box, it is technically both. And that makes no sense whatsoever according to our common sense understanding, but according to the interpretation of quantum mechanics, that is the situation. That is another example of how quantum theory is so wonderfully weird. But why are we accepting a weird theory? Why don't we just say common sense is right? Well, that's because so far nothing has proved quantum mechanics wrong. That doesn't mean it's right, it simply means nothing has proved it wrong. And we've had quantum theory now for 100 years or thereabouts, since Schrödinger and Heisenberg put their theory together. The tools of the trade, if you like, which you can think of as either quantum theory or quantum mechanics, we've been testing it over and over and over and over again for the best part of a century, and so far nothing has proved it wrong, despite the fact that it produces some really weird predictions. That's why we treat it with a certain amount of reverence and say, well, if it goes against common sense, it's common sense that's wrong. Quantum mechanics makes predictions that are impossible by classical mechanics. In other words, quantum mechanics sometimes predicts results that Newton simply could not calculate or could not get right. And if quantum mechanics produces results that appear to be correct and classical mechanics gets them wrong, That's why we believe that quantum mechanics is preferable to classical mechanics when we're describing the world of the very, very small. And it is possible, using our knowledge of quantum theory, to actually build a microscope that can see atoms. What we do is take a very sharp tip, so you can imagine a huge pyramid of which these red atoms here are just the bottom part of a huge pyramid coming close to a surface. And again, the light blue atoms here are just a representative bunch of all of the atoms in a huge sample that could be millimeters or centimeters in size. If we apply a voltage between the two and measure the current with the voltmeter and ammeter there, no current will flow as long as there's a gap between the tip and the sample, according to our understanding of classical mechanics. But quantum mechanics says if d is a relatively small value, although classical mechanics says no current will flow until they touch, quantum mechanics says a small current will flow and will be very sensitive to just how big that d is. Tiny changes in d could give us quite substantial changes in current, says quantum theory. And that has been shown to be the case. We can actually build a microscope on this principle by applying a few volts between a metal tip and a sample made of metal or semiconductor, whatever it may be, and we can verify that the amount of current that flows does depend on d. D, you see here, will vary if we imagine, for the sake of argument, that atoms are sort of spherical, treating them a little bit like billiard balls. We know they're not, but it'll do for the time being. If atoms are small, relatively spherical objects, then the distance d will change according to individual atoms, because the surface is presumably not absolutely smooth, but individual atoms are effectively bumpy, and so the distance d will change as the tip moves from one atom to the next. So if we move the tip smoothly across the surface, over the surface, we can either do what's done on the left, and the varying d will give us a varying current, or we hold the current constant by moving the tip to maintain the same d and measure the current at each point. They're sort of equivalent. And we can build a microscope that works on precisely that principle. The microscope is in the background there. Ignore the handsome scientist standing in front of it. Inside that vacuum equipment there is what I've just described. It's relatively small and it has to be kept in a vacuum to make sure that the atoms and molecules in the air don't contaminate either the tip or the sample and get in the way of this particular quantum mechanical process. So the so-called scanning tunneling microscope, or STM, is inside an ultra-high vacuum vessel where the pressure inside is kept at something like 10 to the minus 13 atmospheres. Hence all of the various gubbins that you can see there in that metal chamber. If we scan the tip over the sample, we get an image that looks a little bit like this. For instance, this is one example taken by a colleague in Manchester. Notice the scale in the bottom left, only 2 nanometers. So each of these little bumps here, the vertical scale has been exaggerated, as you sometimes see with maps, to make mountains stand up a little more from the background landscape. Here we've exaggerated the vertical scale, and individual atoms look like little Matterhorns, little peaks. Notice they are only a fraction of a nanometer from each other. So we see individual atoms, and we also notice that these atoms are arranged in a very uniform way. The atoms tend to line up. Atoms tend to be regularly aligned relative to their neighbours, and notice that they occur in islands. These islands of atomic arrangement are also arranged on a pattern. What is this particular material? This happens to be the surface of rust. This is a surface containing iron and oxygen atoms, and what we think is going on here is that the atoms are more visible in one particular phase of iron, and in this particular region we actually have the same atoms, but they are arranged in a different way and they look altogether flatter. So depending on how many neighbours each iron or oxygen atom has, they will stand out from the background, and in a different configuration they will look rather flat. So we can get an idea of how atoms are arranged on surfaces at the atomic level. We can literally get sub-nanometer resolution of our microscopes. When we do that, we see all sorts of patterns, not only the regular arrays that we see in iron and oxygen in a rust sample. Here's an alloy, and perhaps you notice that when you look at the blobs, in this particular case, white blobs correspond to particular atoms, so they would be high, if you like, in the picture we saw before. Notice that we have particular patterns, like we seem to have petals around a sunflower here, indicating that we have a tenfold, not a 4 or a 6, but a tenfold pattern. And other areas, like up here, we seem to have a pentagon. We seem to have a pattern of 5-fold symmetry. And the more you look, the more you see 5 and 10-fold symmetry of the arrangement of atoms in this particular alloy. So if the atoms are arranged in pentagons, perhaps it's no surprise to realize that when this alloy makes a crystal, it chooses to make a dodecahedral crystal with pentagons on the faces. And that's a direct consequence of the fact that we have this 5-fold symmetry of how atoms arrange themselves when we look at the scale of nanometers. So again, the underlying atomic arrangement is influencing the macroscopic crystals that are made. That was the first clue we had, that a metal that produces this crystal must have atoms arranged like this. And the scanning tunneling microscope that uses itself quantum theory allows us to verify this relationship. There's a few oddities that we notice when we start looking at the distances between atoms. When we look at various distances, well, there's lots of atoms in this arrangement, sometimes pentagons, sometimes these 10-fold sunflowers. When we start measuring distances and the ratios between distances, we find a particular number that keeps cropping up. It's this number, approximately 1.6 and a bit. That's curious because it crops up in other areas as well. If we count how many scales there are on a pineapple, the spirals on a pineapple going one way and going the other way, and we count the number of scales in each direction, the ratio of that gives us a number very similar to this number. And we can do that also on sunflowers, actual sunflowers rather than fake sunflowers. Again, if we count the seed heads going in one spiral and see what number we get, and we count in the other spiral going off in the other direction, one clockwise, one anti-clockwise, the number of seed heads going in the two directions is different. If we divide one by the other, we get this same number again, or at least a number very close to that. So it looks like, for some reason, the way atoms choose to arrange themselves at the atomic scale can sometimes be mirrored by how things are put together on the macroscopic scale. And some people are spending their time trying to understand just why that might be so. One of the most curious images taken some years ago now with scanning tunneling microscopy is because not only you can measure the positions of atoms, but you can actually start nudging them around. So you can actually push atoms to where you want them. And in this particular case, excuse me, some researchers spent some rather patient hours pushing atoms together until they made a corral. So this is a whole load of atoms on a very cold surface which have been pushed into position by the microscope, and then the microscope has imaged the result. So we can see this ring like a ring of mountains all the way round, and it's corralling something on the inside. But what's on the inside? It doesn't look like simply a collection of mountain peaks. It looks like ripples in a pond. It looks like what you would expect if you took a liquid surface and dropped a stone into the middle, you start to generate waves. So in other words, this particular image appears to show individual atoms behaving like particles because they've been nudged around and moved into position. But whatever's going on inside the corral is behaving like a wave, because we get these ripples and we get this interference effect. But this is all the same stuff. It's all a collection of electrons in a collection of atoms. But sometimes the atoms appear to be behaving like particles, and sometimes the atoms appear to be behaving like waves. This is one of the really weird things that you just have to get your head around when you start to try and get to grips with quantum theory. Bohr said, if quantum mechanics hasn't profoundly shocked you, then you haven't understood it. This is a favourite phrase when talking to undergraduate students. After teaching them about quantum mechanics, if they think they've understood it, they probably haven't. But one of my favourite quotes from Einstein is this one. The most incomprehensible thing about the world is that it is comprehensible. It doesn't necessarily behave the way you think it ought to behave, but given time and given thought and given patience and given perhaps a little readjustment of what we think about is common sense, it is possible to get our heads around the idea of how things behave and make up the world around us. We've still got a lot of thinking to do. We've only been doing it for 100 years or so at this sort of level. But the fact that we can apparently start to make sense of the world of the very, very small and how that builds up into the world of the very, very large, the fact that it is possible at all is pretty amazing. Yeah, that's the problem. We do have to do a little bit of thinking. We can't simply take what we're told from quantum theory and just accept that, okay, the maths is easy. Well, no, it isn't. The maths is hard. But the conclusions are straightforward. Well, no, they're not. The conclusions are rather weird. And we have to get used to the fact that we have to park our common sense and start thinking about, yeah, but how do we interpret what quantum theory is actually telling us? I like this image taken quite a while ago because of the scale. The horizontal scale of the image is 850 picometers. A picometer being 1,000th of a nanometer, which is 1,000th of a micron, which is 1,000th of a millimeter. So this is not even 1 nanometer on a side, and we apparently are imaging with this particular scanning tunneling microscope. We appear to be imaging individual atoms, or at least blobs that we can interpret as being individual atoms in this particular structure. If we imagine on this scale how big a grain of sand would be if we're looking at it at this magnification, a grain of sand would be about the size of our moon. That makes me think of the William Blake poem, To See a World in a Grain of Sand. And whenever I see a scanning tunneling microscope showing me individual atoms or molecules, I tend to think of, yeah, we are looking at a world in a grain of sand. I remind you of the poem, and I thank you for your attention. Thank you.